So we're going to work towards our goal of showing that every principal ideal domain is a unique factorization domain. So a principal ideal domain, remember, is a ring where every ideal is principal. Every ideal is generated by a single element. And a unique factorization domain, that's a ring where you can pretend like you're breaking up every element into a product of irreducibles, just like you'd break every integer into a product of primes. So that's our ultimate goal. But in this video, we're going to do two lemmas to achieve that goal. The first lemma, if you have an irreducible in a principal ideal domain that divides a product, A times B, then that irreducible has got to divide A or B. Just like P is a prime number in the integers, prime numbers satisfy this property as well. So let's prove it. I'm actually going to, inside the proof, show that a certain ideal is maximal. So let I be an ideal in your principal ideal domain such that the ideal generated by P is contained in I, and I, of course, is contained in the entire principal ideal domain. I'm going to show that I either has to be the ideal generated by P or I has to be the entire ring. If I could do that, then this ideal satisfies the definition of being maximal. So inside this proof, I'm actually going to prove a slightly stronger result, that if P is an irreducible, then the ideal generated by P is maximal. Okay, so since we're in a PID, the definition of principal ideal domain means if you have an ideal, it's principal. The ideal I is generated by some element A for some A in the PID. Thus, P is in the ideal I. So P is the ideal generated by P is a subset of I. That means P itself is in I. I is generated by an element A. That means P is A times B for some B. Elements in this ring, in this ideal, are just elements of the form A times something else, some other B in your principal ideal domain. Now, P was an irreducible, and I'm writing P as a product of two terms. The definition of irreducible says that one of these terms has to be a unit. So thus, either A or B is a unit. Now, if A is a unit, that means A is a divisor of 1. That would mean your ideal I is everything, because if A is a unit, then the element 1, that's A times A inverse. Being a unit means that the inverse exists in your ring. This is in your ideal I, because A is in the ideal, and ideal satisfies a property that if you take something in the ideal and something that may not be in the ideal and multiply them, you get back in the ideal. So 1 is in the ideal, and once you have 1 in the ideal, it's game over. The ideal is everything. So then the ideal would be your principal ideal domain, the entire ring. Now, if B is the unit, then it'll turn out that your ideal I is just the ideal generated by P, because then we have A is B inverse P, and that implies your ideal is the ideal generated by P. Okay, so this proves that the ideal I is either the ideal generated by P or the entire PID. This shows this ideal is maximal. That's the definition of maximal. The main theorem about maximal ideals is that if you look at the factor ring, you get a field. Now, a field is also an integral domain. If the factor ring is an integral domain, then your ideal is prime. So what I'm saying is this ideal is maximal and therefore also a prime ideal. So now we're ready to prove the actual lemma. So now suppose that P divides A times B. So P divides the product of two things. Thus, A times B is in the ideal generated by P. Divides means P times something is A times B. Well, this ideal is the set of things that are P times something. So A times B is in this ideal, and because it's a prime ideal, either A has to be in the ideal or B does. That's the definition of being a prime ideal. Now, if A is in the ideal generated by P, that means that P divides A. If B is in the ideal generated by P, that means P divides B. There, that's the end of the proof. So we've proved this condition. There's one more quick lemma I'd like to discuss in this video. And after these two lemmas, we're ready to achieve our main goal in the next video. So here's our next lemma. This is known as the ascending chain condition. It says that no strictly increasing chain of ideals, and what I mean by a strictly increasing chain of ideals is that you have a first ideal I1 that's properly contained in a next ideal I2, which is a proper subset of another ideal. This goes on maybe for a while. But what I'm going to say is that no strictly increasing chain of ideals that you see here in a principal ideal domain can be infinite. So if you're in a principal ideal domain, you cannot have a strictly increasing chain of ideals that goes on forever. Okay, the proof of this is kind of nice. It's not so bad. The idea is this. Let I be the union of all of these ideals. So just take everything in your chain and union it all up. Well, then I is itself an ideal. Remember the definition of an ideal. Definition of ideal is if you take I times R, that's a subset of I. You could just prove straight from the definition that this union is also an ideal. It's not a difficult thing to check. So I have an ideal I in a principal ideal domain. Thus, the ideal I is generated by a single element in the ring. That's the property that you get from being a principal ideal domain. That's the defining property. Well, thus, the element A is in I, right? The element A itself is in the ideal. And this means that A is in a union. To be in a union, you have to be in at least one of the sets. So A is in, I, K for some K. It's got to be in one of the sets in the union. But then once A is in the ideal IK, the ideal IK is the whole thing, I. Because if A is in your ideal and the ideal is generated by A, then it's the whole ideal. This means, for example, IK is equal to IK plus 1. You can't get strictly bigger if you're already at the maximum, if you're already at the entire union. So that's the end of that proof. And so follow us along in the next video where I use both of these lemmas to prove that every principal ideal domain is indeed a unique factorization domain. All right, I'll see you there.